and we'll just wait and hope for a few more to pop in.
Yes, we have around 20 registered for the webinar today. Okay, it's 10 o'clock.
Let's start.
So let's start, and we will let people in as we go along. Now Andreas is coming. Okay, I will leave the floor directly to you, Stefan. My name is Madeleine, and I'm one of the hosts for today. Stefan will start.
So welcome to this webinar, Routes to High Integrity Casting, which will cover everything from bicycle parts to electronic casing and probably huge or small things in between. I would say it will be really interesting having this one. We are pretty few today that are signed up for the webinar compared to some of our other webinars. The reason we don't know why, but it will be a better webinar for us participating anyway. And welcome all. We have people from mostly from around Sweden, but also from elsewhere in the world, as you see on the list. And this webinar is part of the WebLearn project that we call this, which is a project funded by the Swedish Knowledge Foundation, where we help and provide cost-effective and time-effective webinars for competence development within the metal and polymer industry. And this is one of our modules which cover non-ferrous alloys. And we have several other modules, and we will cover between 30 and 40 webinars over 2 years, almost with a fortnight between every webinar. So keep a lookout for other webinars. If you found your way in here, you probably have found where to find the other ones. And me talking, that's the one to the left, Stefan Brolin, project manager here at the School of Engineering. And you also heard my colleague, which you will meet later on today in the webinar, Madeleine Zetterlind. But the most important persons today is our guests, our presenters, Professor Lothar Kaljan from Aalen University in Germany, and also from the School of Engineering here, Professor Anders Jarfors, which will present on the topic, which will be interesting. And the format of today is just the intro, which we are almost through, and then we will start with the presentations and also have the possibility to discuss in groups later on, and we will end by 11:30. That is 1.5 hours from now if you are in another time zone. And the format. So if please turn off your microphones if you are not the one presenting. If you have questions, which are most welcome, do write them in the chat, and we will try to answer those questions towards the end. Either write them to everyone or write them to me, Stefan. That is probably the only Stefan in the participant list. And then as the group discussions is an important part of the webinars, please be active in those and give input and share ideas. And the webinar is recorded. So you will get a link to the recording afterwards. So if you don't want to be seen by others online, do turn off your camera. But the discussion rooms will not be recorded. So there we ask you to turn on the cameras. So it will be more easier for the communication and more pleasant for all of us. to get a chance to see a face of each other. I think, yeah, then this is my last picture actually, the Zoom interface. If you happen to be unfamiliar with Zoom, down below you have, to the left, you have the on and off of the microphone and also on and off of your camera. And then you have the chat function, which will open a box where you can write questions. That's about it. And by that, I hand over to Anders.
Yes, thank you very much, Stefan. Well, today I will be talking about routes to high integrity casting, and it's a little bit of a process overview, and you will see a small pink arrow over here and there, and I would like you to focus on that one when you see that one, because then I'm talking about this particular element in pictures that I will be showing. So please, next.
Sometimes this is not. Sorry, Anders.
Yeah, well, no worries. I have all time in the world. So first, I would like to say a couple of words about who I am. Well, I am a Royal Institute student from the beginning, studying material science and engineering. Also have a PhD in metal casting from 1992. I've been working at the Royal Institute with casting between 1988 and 2000. And then I moved to Singapore and worked with manufacturing related questions. I had a small session in a company called MMI Holdings, making hard disk drives and castings, and also gas lasers and some other things with material related issues. Then I've been working for the Corrosion Metals Research Institute in Stockholm for a few years in the middle of the 2000 time. And then I went back to Singapore, and then I also turned back to simultaneously with the Singapore Institute of Manufacturing Technology, also working at the Nanyang Technological University. And since 2011, I am with the Jönköping University. Even though I have a couple of other activities in Nanyang, in Singapore, and with the Chinese Academy of Machinery Science and Equipment Development in China, and also with Cranfield University. Research focus-wise, it's metal casting with reo casting, solidification, and defect formation as the main topics. And from material science standpoint, I work with composite materials, mechanical properties, a bit of fatigue, rheology of metal slurries related to reo casting, of course, a little bit on formability and workability. And recently also sustainability has come in as a very important part, where we're looking at manufacturing and energy efficiency and process yield. And I do enjoy cycling. So when I'm not in the office, I'm probably on the road. So we can take the next. So high integrity casting, why is that an important part of thinking? And we had a little bit of a pre-discussion where something like this to the right we can see, and that is a vision of the future car, which consists of one casting in the rear and one casting in the front, and a battery sandwich design in the middle. So that is one of the trends that we see happening. And of course, this puts completely new requirements. We know that from the beginning, we had a bit of downsizing with the fuel crisis. But everything that has to do with lightweighting and downsizing in terms of weight means that it's material reduction, material substitution. And we're also talking about cost effectiveness today. And that means that the castings, instead of joining many small parts, you can cast and functionally integrate in casting. And this means that defect management becomes very important, because we want ductility in the parts. We do definitely want to have crash safe cars, and also We do not want to have a lot of scrap, because if you cast something which is as big as a quarter of a car, it's of course a lot of cost in that, and we definitely want to have high process yields. So there are many different ways of achieving high integrity castings. If we look at it from a productivity standpoint, most of the casting process is capable of doing sufficient volumes, as for instance for the automotive industry and for the electronics industry. It is pressure-driven casting processes. And when you look at the ability to create a high integrity casting, we have the pressure in the die cavity as one of the parameters, because we can suck in the melt, or we can empty the cavity, because the atmosphere in the cavity is one of the problems. We can work with the pressure on the metal side, that means increasing the pressure. And the difference between the cavity and the metal side is also very important, because that sort of drives the filling process. We can also work with the melt properties in order to change the behavior of the melt. And again, what you will also see from Lothar a little bit later today is when we look at optimization of the process and diagnostics and things that you can do with modern technology. So next, please. So one of the most standard processes that we have for high quality castings is low pressure die casting. And in low pressure die casting, you have a furnace cavity or furnace compartment, which is hermetically sealed, and you increase the gas pressure. And that means that you force up the melt through the stalk into the actually die cavity here. And looking at this, in order not to have a turbulent fill, you can calculate using the Weber number a critical speed, and you end up with about half a meter per second as your fill speed. For low productivity processes and short fill lengths, this would be quite sufficient. But when we're talking about casting a quarter of a car, you need much higher speeds in order to do that. So we can take the next. There are some ways of improving the low pressure die casting process, and there are the vacuum riserless and the pressure riserless casting system. So for the vacuum riserless system, you have a hermetically sealed compartment above the actual die system, where you suck up the melt through vacuum into the die cavity. There is also the pressure riserless casting, where it's a little bit just as for the low pressure die casting system, a compartment where you increase the pressure and you force the melt up. The difference is that in the low pressure die casting system, the melt level is varying, but it does not do that in these systems. And that means that the variation from fill height is eliminated. So that means that you have the same pressure drop when you fill the die, and that creates a little bit more reproducibility. But again, keeping the level constant and having a way of transporting the melt in is a little bit more complicated here. So we can take the next. There is another way you can do, and that is the counter pressure casting. And that is working in the same way. You have a system where you pressurize the furnace chamber, and you have a hermetically sealed compartment around the actual die itself. So here you can pressurize the chamber, forcing the melt up the stalk, but you also can work with the super pressure in the furnace in the die compartment. And that means that with increased pressure in the die compartment, you can get a more quiescent type of fill during the process. melt breakup is not as likely as it would be if you have vacuum, for instance. So that is one way of managing this as well. And you can work then with the pressure difference between the furnace compartment and the die compartment. And this again is to control the fill. And that means also that by varying the two pressures, you can also control the speed during filling, because speed during filling is essential for all these casting processes. You can take the next. So, of course, talking about these, all the high pressure die, all the low pressure die casting processes, they are for normally larger car parts like wheels and such, and they have moderate productivity. If you really want to have a higher productivity, you need to use high pressure die casting. And high pressure die casting is essentially working in a way where you, instead of pressurizing the furnace compartment, you pressurize the melt directly with a piston. So that means that instead of working with the furnace, you have now a hydraulic system, and you can increase the pressure significantly. So the new variant we have here is really to work with the melt side pressure. And that means that you can squeeze and reduce the size of porosity. And there are ways also where you use extreme pressures like squeeze casting and liquid forging. You can also work with reduced pressure on the cavity side. And here it's not really having a counter pressure, but more evacuating the chamber itself in order not to entrain gas during filling. But then again, there's a lot of work in order to control turbulence, and there's ways also to work with changing the viscosity of the melt that we will come to. You can take the next. So one process is squeeze casting, and that is really increasing the pressure on the metal side. And there are two main processes. You have the direct squeeze casting process, where you pour the melt into a shot chamber, and you directly act into the, this is indirect squeeze casting, where you pour it into the shot sleeve, and you force it into the die cavity. Indirect squeeze casting, you can have multiple dies. And this is an example where you have an inlet, you have runners, and this is two high performance safety components. And this is done because you need them to be completely pore free. So we can take the next, which is then direct squeeze casting. And the difference with direct squeeze casting is that you do not have a plunger moving the melt into the die cavity, but you pour it into the die cavity, and you have a punch from the top, just like a forging operation, where you actually squeeze the melt under high pressure. And this gives you something which is very pore free. And experience says that if you reach about 50 megapascals in actual pressure in the die cavity, you will get a pore-free structure. There are ways of working with this, and this is one example from a process called liquid forging, where the actual geometry is sitting in the punch itself. So this is formed like a backward extrusion process. And these fins that you see here, they are 6 centimeters high and about 1 millimeter wide. And they can be cast in many different alloys. In this particular alloy casting, it is 6061, so it's a wrought material. And you can actually bend these fins around their own radius. In general, when you look at the common materials that have been squeeze cast, you can see that you get decent property, but foremost you gain on elongation. The issue with this is that size is, of course, a problem in squeeze casting because you need very large machines and such. You can take the next. Another way of dealing with all these quality issues is that when you do fill in high pressure die casting, you end up having gas in the actual die cavity, and that comes from the air. It comes from die release agent that you spray into the die chamber. And there are many very different ways of managing this. One process that has been used more in lately is the vacuole process. And the vacuole process is actually emptying not only the die cavity, but it also empties the shot sleeve, and it's also in a way connected all the way down into the furnace compartment. And you can reach as low pressures as 10 millibars in the die cavity. And this means that if you entrain any gas inside the die cavity, that means that it will not sort of cause a problem. There are alternative processes like this. The high Q cast is one system. You sort of empty the shot sleeve, the runner, and the gate system. May also reach 10 megabar. Another one, millibar. Another process is the Fondor-X process. This is quite common in Sweden actually, and you can also empty the whole system. This has a little bit lower end pressures than what you would have with the high Q and the vacuole process. But what you will do in these processes, you will reach the 0.5%, which is the criteria for a high integrity casting. So we can go to the next. Now, in all these processes, the die release agent can definitely cause a problem. And I would like to show you here one little example, because it's not only the pressure in the chamber that is important. This is from a study with a foundry that had a problem on rainy days, where you had a very large rejection rate on the rainy day, but on the sunny days, it worked like a charm. And it turned out to be so that it had to do with the evaporation rate in the die, and there were some clearances between different parts of the die where you had die release agent getting stuck. At this point, you can see you have a bubble trail moving through in the same direction as you have the fill direction. And these little bubbles, they have been pickled. We pickled away the surface so that we could reveal these types of porosities that you would find. And this is one of the problems. So vacuum does not really solve all the problems, but you also have issues with die release agent and the use of that. So you end up, when you want to do high integrity casting, with a very complex situation. I will come back to that. We will come back to that later. You can take the next. Now, another way of working with this is to look at semi-solid casting. And this equation, it may not be very famous to many of you, but this is from Albert Einstein and his thesis, and it's Under Bestimmungen der Molekyldimensionen. And he studied slurries in his early days. And he developed an equation for viscosity where this Fs is the solid fraction. And this is for dilute suspensions. And you can actually use this concept by understanding that if you have a certain portion of solid, you will increase your viscosity. And that means that if you abide by rules such as increasing the viscosity to maximum that you can, which means using the highest possible solid fraction, that means that you we get the highest viscosity, which would be a turbulence reduction. You can also use, in order to enable fill, you need to use the highest possible die temperature because it aids the filling. And you can also then reduce the fill speed. Even though you use a high pressure die casting system, you can significantly reduce the fill speed in semi-solid casting. And that means that you can reach a defect-free material. And there are some examples here from Metals Handbook and also from Yesada Wanasin, who works with the GIS process. But as you can see, there are some extreme examples being displayed here by Stephen Midson in the ASM handbook, where you can have in T6 treated condition also very good elongation. And you also have a relatively wide alloy selection here. One should take care here that you cannot do this for eutectic and pure metals effectively on large scale. So that is a limitation of this. So it depends on your material selection. We can take the next. Now, looking at this, there are some additional advantages. If we set 0.5% here as porosity, and you compare conventional high integrity casting with Rio casting, combining all the possible means, yes, using vacuum and high pressure die casting, Rio casting and vacuum. And this is the end pressure of the machine, the intensification pressure at the end of the fill. You can see that in order to reach this 0.5%, you need a lower end pressure for Rio casting, which is a lower line, than for the upper line, which is conventional casting. And that means that you can actually cast the same part in a smaller machine because you require lower pressures. And that means that in terms of supply chain, you don't need the largest machine available, which would be maybe, if you take the 6,000 ton machines, it may be 10 machines available in the world. But if you can do that in a 4,000 ton machine, there is much more machines available. So that is also supply chain support. So we can take the next. Now, there are also some other bits and pieces here. I just wanted to show you this here, which is the fill length, and that means how far you can fill. If we know that we can change turbulence, and we look at the fill speed, knowing that when you have at least 30% solid phase, your heat transfer coefficient, which is H here, is about half of that for conventional casting. And that means that if you lie in the range between 30 and 50%, you get better fluidity as well. So that is also another argument for also working with viscosity modification as means of making high integrity castings. So we can take the next. So in general, I would like just to summarize this initial part, saying that if we look at low pressure strategies, the important part there is really to allow a slow quiescent filling. And that is by controlling either the actual pressure increase or the pressure difference between the die cavity and the furnace side. If you go to high pressure die casting, you have many more strategies. You have high pressure solutions, including squeeze casting. You get a very high quality of the casting, but again, you still suffer a bit by productivity because the squeeze casting process has a limited cycle time. You have vacuum solution, and those give you very good quality, but you also have issues with die life because you still need to use the same type of die spray. You have off-gassing issues. If you use viscosity modification, you will get a die life improvement because you carry less heat into the die. less heat into the die means that you can reduce your release agent usage, and that means that you have less issues with off-gassing during filling. And you can also fill longer if you're in the range 30 to 50%. And it's possible to combine this with vacuum solutions, but you would probably need a new gating design. But there are a number of various process selection or process routes in order to solve your production problem. But again, knowing that, you need to understand your process. And I think that I will sort of move over, and maybe Lothar will say something more about how you can control your process. Because in all these processes, you need to be able to control your process. And all these solutions have their own intricacies.
Okay, thank you very much, Anders. Now we will move on to Lothar. I don't see any questions right now in the chat, but you have the possibilities, of course, later on. So Lothar, please, the stage is yours.
Okay, can you see it?
Yes.
And you can hear me, obviously. Super. My name is Lothar Kalin. I'm from Aalen University of Applied Sciences in Germany, and I'm going to talk about how to control the process a little. And I have some nice pictures again, because foundry is something old-fashioned stuff, but since we have electro cars, and not only from BMW, the i3, but also the Tesla you have seen, so we are up in everybody's mouth, because we are happy and may be able to make lightweight, thin-walled parts, which can substitute steel parts. Sheet metal parts is my favorite overhead from Audi. 10 parts substituted by one aluminum part. Here you can see in high pressure die casting gives you a weight reduction of 10 kilograms per car. That's huge. And this is just a very new picture. I just added it because it shows from the new Tesla. The old one left side is 70 parts, and he is going to substitute it into one part. And what you need to do this, of course, is a huge machine. Anders already mentioned that it's a 6,000 something ton machines, and it's very huge. And Tesla ordered the first machine which has more than 6,000 tons of locking force. That's crazy, but Elon Musk can do it. Okay, what are we doing in our lab? We have a very nice lab with 3 high pressure die casting machines. We can do sand casting, permanent mold, and we are do research on salt cores in high pressure die casting, gas injection in high pressure die casting, and carbon fibers, and we can run aluminum, mag, and zinc alloys. And here you see our middle machine, 400 tons, doors closed. We have automatic spraying. This is a parting agent Anders was talking about. We have a new system to dose the metal into the shot chamber. This in this case is aluminum, but we also can use vacuole and magnesium and all that stuff. And so this is the plunger. The shot is coming now. It's moving relatively slow at the beginning, but fast during filling to get very short fill times. And then we can open up the die and have a very nice part, which is taken typically by a robot, again in an automatic production cell, but here we do it manually. And what is very interesting, I can show you here in the hand. This is the best we all did. This is a housing of an electromotor. And this electromotor is for an i3. It's a demonstrator only, I must say. And the cooling channel we put in by blowing gas with a lot of pressure, nitrogen in here, and all the liquid melt is blown out on the other side. And this is a length of 2 meters and 35. So this is, I think, is unique. The only people doing this crazy stuff is here in Aalen. Okay. But now we come to the 3 phases. The first phase, the metal is put slowly to the gate. And the second, we have wave formation, pre-solidification. A lot of problems can evolve. Second phase, where we have the metal shot into the chamber, into the cavity, very short fill times, 30 to 50, maybe 70, 80 milliseconds. And then we have the third stage, where we can get shrinkage porosity. We apply a lot of pressure just in order to feed and have no porosity due to shrinkage in the part itself. What do we control today? Basically not a lot. We have a temperature in the holding furnace. We have the injection unit where we at least have a shot profile. Lubrification, some only minor people do it, and die thermocouples, I don't think a lot of die casters use it. So what we get is this shot profile, first stage, second stage, third stage, pressures and velocities of the plunger, and then we can calculate the velocity of the melt and stuff like this. And we can get a lot of information from this. But the dream of a high pressure die caster is to understand the process. And this is what I'm going to talk about in the next 20 minutes. What should we use? Control much more data from the evacuation, from the die cast machine, from the lubrification and everything. But the problem is we have so much data now, we need to kind of understand the data. This is going to be the problem. And we had a project, it was called Music, long time ago, where we tried to get a cognitive system where we get all the data in, but then you also need quality data. And this will be the thing we talk about also, to understand and then control the process with this. So we have a lot of process parameters, and the process parameters are a lot. We have, some people say 200 parameters in high pressure die casting: piston speed, first day, switch points, holding pressure, mold temperatures, flow rates, cooling time, and. You can talk half an hour about every process parameter here. But also the other parameters I just showed, I think, or we think we can control them. But we also have parameters like these. They change during the process. Piston wear, or dosing is changes, or gate wear, or furnace temperatures vary because people put fresh liquid metal in with another temperature, changes the process as well. Variation and so we can talk about parameters again for a half hour at least, only about those which change. So the big thing is we have a lot of process parameters. Now we need sensors to control it, because later quality analysis in the forecast is a goal. And we have a very large amount of sensors because we have a very good company in Germany. It's called Electronics. If you're interested really in sensors for high pressure die casting, talk to Mr. Gauermann. He's the owner of Electronics, and we work with Electronics together since a very long time. And they are a very innovative people and have, as you can see, a variety of sensors. And I'm telling you about our experience with sensors. The first thing on the left-hand side here you see is cavity pressure sensors. And I think that's very important because you only calculate pressures from the third stage, plunger pressure, into the melt. But now you can see with these cavity pressures, which hold up to 2000 bar, and they last a very long time. We never made 100,000 shots with them in the lab, but I think they do at least last 10,000 shots or something like this. So they're ready for industrial application. You get information about cavity pressures of inside the die, and this really is important for the quality of the part. On the right-hand side, of course, you have classical hydraulic pressures, which are used for a conventional shot chamber, shot profile already today. What is also new? Metal front contact sensors. For our gas injection process to produce these parts, we need to know exactly when is the metal where. So we can build in sensors which have a little contact, electrical contact, and you can see, you can see here 3 sensors in these points giving you different signals. And you can, for example, also control simulation. Is the simulation you made with Magma or another code, does it fit to your real experimental idea you have in the die? What is happening there? So this is also very interesting and not very difficult to install. Also, die temperatures, very crucial for the quality of a part is the metal temperature, but not only the metal temperature right at the surface, but also inside the die. And Electronics offers a sensor which gives you multi-distance reading. So right here, right here, and this shows you the reading you get out of it. On the left-hand side, you see the temperature curves. We are not yet in what we call quasi-steady state. And this is a temperature right at 0 millimeter, blue, right surface temperature of the metal, basically. And then 3 millimeters in depths of the die, we have the green curves. You see a big difference. And then we go 30 millimeters. You can see only down here that the die is getting hotter and hotter. So you can control, are you in steady state? Do we have some problems with too high data of the die temperatures and stuff like this? But again, until now, not a lot of people are using it. And I don't understand really. The die temperatures are, of course, very much controlled by tempering oil. You have oil or cooling and heating systems near close to the machine, to the die, and you put them on 90 degrees or 180 degrees, and you assume the die now will have, after a certain time, will also have 180 degrees. But nobody controls really the flow. Is it oil really flowing into it? And I think this is very inexpensive, very good usable tool to control oil flow, not only temperature, but the flow rate. Anders already mentioned vacuum. This is very important, and we use vacuoral process, but also classical standard vacuum processes. And what the people measure here is only basically the pressure in the cavity. But here we have a multi-vacuum pressure, and it measures the air mass, which you take out of the mold, the vacuum, the pressure, the humidity of the air, and this is very important. It's a very innovative new sensor, but I show you some results, and residual gas. And what we see here is for a shot curve with vacuum air showing no leakage. You can see here in this sensor, and this is the air mass. It's not the pressure. Vacuum pressure is the green line, and the gray lines are just piston speed and pressures. And here you see the same with the leakage rate, and you can clearly see a big difference, which does not show up so clearly in the green curve, but the mass, the air mass, clearly shows the difference. Sorry. And of course, we measured also densities, and this is clear, no leakage, and leakage, you get a big difference in density of the whole part. Also, if you have a dry mold, parting agents are typically put into the die with water. The water is assumed to be evaporated by the heat of this die surface, but is it really true? And you can see the vacuum pressure down there shows always this different colors are different 10 shots behind each other. And you can see the vacuum pressure shows always the same. But if you can see here the humidity of the air evacuated, it shows a big difference. The shot one, the die maybe was not that warm yet, has much more humidity in the evacuated air than shot number 10. So you can see clearly there must be also a quality difference between the 10 shots, which would not be detected by the pure vacuum signal. So that's a big difference. And now I show you one where we have a wet mold. So we do something not correct, right? And you can see after shot one, the humidity goes up like crazy again. And even after shot 10, there's a big difference now between shot 1 and shot 10. What else do we have? We're talking about spraying. This is also important that we have a flow rate sensor for the parting agent. That's available since a long time, but again, not a lot of people use it. And we built it in, and I can tell you it's a very important thing to control this. And you can also, I will come back to it later, see the difference very clearly of the flow rate in the infrared camera picture of the temperature of the die surface. Another sensor we use a lot for parting agents control. Some people come and say, oh, can you give us an idea how different parting agents work? One is better than the other, but do you have numbers? And we developed a tool where we measure the ejector forces. So we have pressure sensors, as you shown here, behind the ejector pins. So when we eject, we can measure the pressures and get an information about what is happening. Of course, we then also again measure the shot force in during the shot, third stage, then the die opens, but here the small one, and if you widen the signal, you can see big, large differences between different parting agents or parting agent processes or things like this. So this is a very important tool also. I'm not sure whether it's usable, which makes sense for control, but the maximum value, for example, you could use for a standard control in an industrial process. Another thing, another company, MoTool has developed, but I think it's available from other companies now too, is also a spraying control unit, and the signal is infrared dye signal. So they take the temperature of the surface of the dye to control the parting agent flow, but also the air blow. The time and amount air blowing costs a lot of money, and this costs a lot of time and cycle time, and nobody wants to do it. But you need to prove that your dye is really dry, because otherwise you get real quality problems. That's a real issue here. Too cold, of course, gives you cold shots and stuff like this, but it's also not so easy. What we did was, in our tests on this test casting you already see here, not measure the whole temperature, but we concentrated on these small little red areas. And the red areas were taken for process control or for process monitoring. And we always take a picture immediately after extraction of the casting and at the end of lubrification. That's very important. So you can see what is happening with the dye. Does it change in your process? And then for control of changes, maybe you only need 1, 2, or 3 areas of control, not so many as we used. Of course, if we are talking about infrared, there are a lot of things to control. It's not a Lambertstrahler. It's some areas are more black, others are more shiny, so you get different temperature readings. But that's not really the problem, because you only want to have a relative signal to the shot before and the shot after. So I think you can use this very nicely. So we have a lot of sensors, and we have this seen before. We have just 3 curves. It's the velocity, the pressure, and the stroke of the piston. And now we have something like this. And nobody does it understand anymore, because it's so complex and so confusing for a lot of people. So what do we do? And the only other thing is we have the signals. We need to control it and put it together with the quality. And just to show you, this is the real casting we use for a lot of trials for this. And this is a casting where we built a lot of defects into it. Distortion and shrinkage porosity and all other stuff like this. And just to see cold shots, what is happening. And we put a lot of sensors in here, metal front cavity sensors, metal front and sound sensors and other stuff like this, just to check what we can see. Do we get more information? And it was done in the frame of a European project, music, a lot of this, but this ended long time ago, but we are still working on the problem because it was not solved. And again, you get a shot curve, switch point, and you get a piston velocity. This is what we know, maximum pressure, but now we get a maximum piston acceleration. We get a maximum melt temperature, a mold temperature, a cavity pressure at this position, a maximum pressure, another solution, a vacuum pressure, and you can see is a lot of data coming together. And to understand the data, we need to evaluate the data. And this is one of the things we have in the earlier stages of our analysis taken only maximum data. So we have a curve here and we take the maximum mass rate evacuated air, or the maximum metal contact temperature, or the maximum cavity pressure here. But maybe it's how the whole curve looks. And this is what we are working now in the frame of artificial intelligence. We want to analyze the whole curve, because we think the first derivative, how fast does the metal contact temperature goes up, also gives you very needed information about the quality of the part. So, but this is not yet finished. We are still working on it. Until now, you have to take all this data, extract maximum data or the points of the curves you think it's important, and produce a flat table out of it. And then you can get with this flat table, you can use it and go into your DOE and try to get information which is connected to quality. And quality, we did visual inspection, bending tests, computer tomography, which is very slow, distortion measurement, and other stuff like this. And you get a big correlation matrix between the process parameters, sensor data, and quality. You can see. And red here, you already see this temperature gives an idea on the density of the part or whatever, but it's not so easy to do this. But with DOE, you can get also effects, and that's very interesting. For example, in this case, with the cold shots. Cold shots, you can see also from the simulation here, if it starts to solidify, it will look like this. It's much better on the right-hand side. You can see the melt temperature, of course, everybody understands easily, and the fill time have a big impact on cold shots. But with DOE, of course, you can get also values in between, which if you do not have a linear combination of effects. Or you have maximum temperature of the sensor temperature 1 and the piston velocity, giving you again a quality index area in this section. And this was the sensor up here. And this is very clear. You can see strong impact of the sensor T1 on here, the quality index. Or same for bending. I'm going over this a little faster. Or maximum pressure in the third stage, and the machine pressure, of course, gives you density information on which is in the dome, which you can see on the right-hand side because this is X-ray or computer tomography. We do have a computer tomography, a very new one, as you can see here from Zeiss. I'm very happy to have this here, where we can have excellent information about the quality, but it's too slow. We need something faster, much, much faster. And this is also where we stand now. And I show you the first results of what we are doing now to get over this. Years ago, 2016, we also had the idea to get faster information about the part quality, not with density measurements. You do not have enough students to do that. Computer tomography, you need half hour for each analysis. But we do in high pressure die casting, we do parts every 30 seconds, one part. So this is what we have in mind right now. This is a sink machine. Our sink machine with 125 tons is a hot chamber machine, what we try to do. We have this part here, and on the surface of the part here, we can create cold shots. And we have the cast part, and we take a camera picture in a special dark room. It's a small box, as you can see here, under special light, so we see it all the time. And then we get a surface image. And we want to put the surface image now into a neural network and understand, aha, is it a cold shot or is it not a cold shot? This is by teaching the neural network. If it's a good part, everything is okay. If it's a bad part, of course, we have to adjust the parameter. But just a camera picture, we found out it's not so easy to understand or teach a neural network. So if you have the original, we need to apply some filters and an edge filter. And you can get from this picture left to the right, where you have some lines. And the lines, we hope, show somehow it's a digital version of the formation of the surface. We want to see the cold shots. And we have no cold shots in the upper section, but you can see here in the lower section, we have a different image, extracted image. And we want to teach with this now the neural network. And it's not only the visual inspection of the surface, but we also do it with X-ray, because X-ray is not computer tomography, it's just X-ray is relatively fast. And we can get an X-ray image. But here also the X-ray image looks like this. We have visible porosity. We need to extract more or less a digital version of the left-hand picture. And that can a binary black and white thing. Of course, you can make a lot of mistakes. This is also not so easy to do this. And this is what we're trying right now, not to going from this point to this point and lose information. But this information is easy to take over into this edge filter thing. And then we can, again, give it to the neural networks. Clearly, defects clearly visible. This is the goal. So I've taken you from process parameters to sensor data, to quality analysis. Again, this is, I think, very important to understand. If you have sensor data, it's not industry 4.0. If you have understood the quality connected to your sensor data, then it starts to get the industrial application 4.0, as we call it. And of course, the final goal is here, the forecast at the end of everything. And I think this is about it, and I'm happy to answer some questions. Thank you very much for listening.
Thank you very much.